this is Shivakumar. Today we are going to discuss about logic gates, right? So whenever we are going to discuss something, first we need to know the meaning of the title. So here our title is logic gates, right? So logic, where do we use the logic? To think, logical thinking, right? And here we are using gates. Gates, we are having the gates, right? So gates are used to open or close, right? So we can think that here the logic gates is nothing but the open or close of the gates logically, right? So the gates are to be open logically, then we can call that is logical gates, right? We can think like that first, then after we'll move further. Okay, so this logic gates comes in our electronic devices. We are going to use the logic gates in electronic devices, right? So electronic devices, so they have the circuits, electronic circuits. So we are having two types of electronic circuits. What are they? Electronic circuits are having two types. Electronic circuits. Electronic circuits. Circuit is also represented like this, CKT. It is a short form of circuit. Okay. So electronic circuits. So electronic circuits are having the two types. First one is analog circuit. A-N-A-L-O-G. Analog circuit. Right. Next one is digital circuit. Digital circuit. So what is this analog circuit and what is this digital circuit? So let us take watches. We are having the two types of watches, analog watches and digital watches. So I use analog watch here. I am using the analog watch here, right? So this analog watch, what happens? The seconds hand, hours hand, minutes hand is rotating. So for that reason, what happens? We are going to get the signal in the analog form. That means continuously it was there, right? And whenever we see the digital clock, then what happens? We are going to see the digit is going to be changed within the fraction of times. So then what happens? There, here we are having the continuous form, and there we are going to see very fastly, right? We are going to get the result very fastly over there, right? So we are not going to see the continuous form there, but we can see the continuous form in the analog form, right? So for that reason, we can write the definition of analog circuit and digital circuits. So first write the definition of analog circuit. Okay, so analog circuit is the waveforms are continuous. The waveforms are continuous, and all value of signals, and for all values of signal, are possible. So here what happens? The signal will be like this, continuous form. So this signal may be voltage or current. Voltage or current. Okay, so let us consider in electronic circuits, right? So for that reason I am using voltage or circuit, voltage or current. Okay, so here what happens? The signal of that, here we are going to get continuously increasing or continuously decreasing. Here what happens? It is not breaking. It is not breaking. Here we are having continuously moving, right? So it is continuously moving means, so for that reason we can say that is the circuit is the analog circuit. Next we will see the digital circuit. So the digital circuits, the waveforms are pulsating waveforms. Pulsating waveforms, right? So in digital circuits, the pulsating waveforms is going to be observed, and the discrete value of the signal, the discrete values of the signals, discrete values of signals, that signals may be voltage or current, right? So here what happens? Here we are going to get the continuous waveform, continuous waveform. Right, and here discrete values of the signals. For here what happens? For all values. For all values of signal. For all values of signal. But here discrete values of the signals. Okay, so the digital circuit having pulsating waveform. That means here we can take that the pulsating. So if it started with 0, then it will move to up and it continuously will. If you take some voltage and it will come back and it will move, come upside, move, down, move like that. Or else it can also be moved like this. You can also move like up, down, and here what happening? Here the continuously it is not moving. So here what happened? Discretely it is very fastly it is coming downwards and very fastly it is moving upwards. And here what happens? Here we are having the continuous form. Continuous form is there for the analog circuits, and for digital circuits we are going to get the we are going to get the pulsating waveforms, and we are going to get the discrete values of the signals. So these are the signals of voltage or current, voltage and with respect to time, and here also we can take voltage and with respect to time, right? So these are the electronic circuits. Those are analog and digital circuits, right? So in that we are going to discuss about the digital circuits. So digital means there we are going to get the pulsating waveforms and discrete values of the signals. So there in the digital circuits we are going to use the logic gates. So what are the uses of the logic gates? Where we are going to use the logic gates, and how many types of the logic gates we are going to have? So we are going to discuss now. Okay, logic gates which possesses the digital signal in certain manner. So logic gates which possess the signal in particular manner. So we are going to use the logic gates. We are going to use in calculator. In calculators, digital watches, burglar alarms, and we are going to use in ICs, integrated circuits. So mainly we are going to use IC 555. We are going to use the logic gates mostly we are going to use in IC 555. The logic gates are going to be used in IC 555, and some sensing objects, sensors, let us write sensors, etc. Okay, so these logic gates are used in the calculators, digital watches, burglar alarms, ICs, that means integrated circuits. So every phone is having integrated circuits, right? And sensors, etc. We are going to use the logic gates. Okay, right. So here you see digital circuit. So digital circuits are going to be used. The language of the digital circuits are binary language. So the language of digital circuits can perform, or digital circuits language is binary language. BINARY, binary language. What is this binary language? Binary means what? Binary means 2, right? So binary language, that means 0 and 1. So the binary language is 0 and 1. So here we are having the 2. So for that reason, binary means 2, right? So here we are having 2 objects, sorry, 2 numbers, that is 0 and 1. So this 0 indicates off and this 1 indicates on. 1 indicates on, 0 means off. Right? Okay. And it is also open circuit. Open or it is closed. So 0 is open, 1 is closed. For binary language we are going to use. Right? So here we are using the logic gates, right? This logic gates. So the logic gates are those gates which have the one or more inputs. Then we get the output only one. That is not this one. Okay? So inputs is represented like this in electronics. Okay? Inputs for logic gates are one or more than one, but we get output only one. That means let us take a device, the X device. I would like to take X device. Okay, so I am giving 1, 2, 3 inputs. So input 1, input 2, input 3. 1, 2, 3. But here from outside we are going to get only one output. So here we are going to get only one output. So here we are getting 3 inputs, but here we are getting only one output. One means not only this one, not this one. Okay, right. We'll see. So I would like to ask you, what is 1 plus 1? What is 1 plus 1? 1 plus 1 is equals to 2, right? But in our logic gates, we are going to use 1 plus 1 is equals to 1. Why? Why? We will see. So this was explained by the scientist named called George Boole. He given the algebra called Boolean algebra. Boolean algebra. Okay? Boolean algebra. Right. Okay. So why 1 plus 1 is equals to 1? So 1 means what? On. Right? Another one means 0 means what? 0 means off. Right? So let us take a circuit. Okay, let us take a circuit. So here we are having a switch, and here also we are having another switch. So here I just applied some voltage here and having some resistance here. Okay. So here we took a bulb here. Right. So here what happens? Here these are my inputs. This is input 1, input 2. Right? Okay. So what I said, 1 means on, 0 means off. Right? Okay. So here I would like to on this. So I give 1. Right? I give 1 this here. So then what happens? This bulb will blow. Right? And if I off this, then what happens? This bulb will blow. So 1 plus 0 is equals to 1. And if I off this and if I on this, then what happens? 0 plus 1 is equals to 1. This is on state, right? It is in the form of on state, right? Next, if I on both, then what happens? 1 plus 1 is equals to 1. So it is blowing. Blowing means what? It is in the state of on. That means closed circuit. Okay. So here what happened? If we on this or this, any one of this, then we are going to get 1. That means on state. So by that we given some algebra. So we know that 0 and 1 are called bits. In binary language, we are going to use 0 and 1 only. right, to express anything, right? So here we are having 0 and 1. So by using these two, we are going to write the Boolean algebras. Okay. So first we'll see the addition. So addition. Okay. So I would like to take two inputs, right? So here let us take input A and B. I am taking inputs. So my output I am taking C. I am taking my output. Okay, right. So in addition, so let us take A, B. So A plus B. So A plus B is equals to C. Okay. So here in the place of A, in the place of B, I would like to take this bits 0 and 1. So 0 plus 1, or else I would like to take 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. Then we are going to get 0 plus 0 is 0, 0 plus 1 is equals to 1, 1 plus 0, 1, 1 plus 1, 1. Okay, so here we got the addition of this Boolean algebra, we got like this. Okay, so whenever we are having this in general form, how do we write? So we can write this in the form of A plus 0. A plus 0, then here we are going to get A, right? A plus 1, here we are going to get 1. So in the place of A we can write 0 or 1. Okay. So then we are going to get, in the place of this here we are going to get A, and in this place we are going to get 1. Okay. So this is addition. Now we will see the multiplication. So here also I would like to take two inputs and one output, right? So two inputs and gives one output. Okay. So here also I would like to take A and B. Then my output is equals to A dot B. So here we are going to get, I would like to take the output as y is equals to A dot B. And here I take C, right? So in the place of C, I would like to take y. Mostly we will take y. Okay. So we can also take C also. Y is equals to A plus C. So A plus B. Okay. And here you see, here we are having 0, 0, 0, 1, 1, 0, 1, 1. Okay. So 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. So it is like general algebra, right? So here what happens? Here we are having off, off, and here we are having on. So for this we are having a diagram. So let us take the diagram like this. Okay. So in this place we are going to take a bulb. Okay. So here what happened? This is my input number 1 and this is my input number 2. Okay, input number 2, input number 1. Okay. So if I on this switch, okay, if I on this switch, first switch, then will this bulb glow? No. Right? So if I on this switch, then the output is 0. So if I on only this, not this. If I on only this, then will this glow? No. Why? Because here we are having an open switch. Right? Whenever the two switches are on, then we can get the output here. Right? So here what happens? 1, 1. Then here we are going to get 1. Right? So for this, we are having the diagram. So this diagram can be used for the addition. Okay. Next we will see, here we are having addition, multiplication. Next we will see complement. What is complement? Complement means the invert. So let us take complement. complements. So let us take, here I would like to take A. If I give the input low, then I will get the output high. If I give the input is high, then I have to get the input low. Okay, so let us take A. A is given, then my output will be A complement. That means if I give 0 input, 0 is my input, only one input I am giving here, okay? So 0 input I am giving. Then I am going to get the output as 1. So 1 is my output, my input is 0. Input is 0, output is 1. So if I give input as 1, then my output will be equals to 0. So this is complement of inputs. Complement of inputs. Complement of inputs. Okay, next we'll see double complement. What is double complement? So if I give A here input, A is my input, then if I give the A is input, then my output will be equals to A bar, right? So this A bar, A complement, let us call complement. So A complement, I would like to give another time complement, then this will become A double complement. A double complement means nothing but the input same A. So input and the output both are same. So let us take here complement means first one is like this, right? So this is upside, this cap is upside, right? Right. So if I give the complement, then it will get like this. If I give again the complement, then it will move like this. So then what happens? Compared to the first one, and now both are similar, right? If we give the double complement to any input, then we are going to get the same output. Okay, so if I give the one complement of the input, then we are going to get reverse. That means if we are going to give the low input, then we are going to get a high output. If we give the high input, then we are going to get the low output. So basically this complement is works under common emitter transistor. Common emitter transistor. Now we'll see commutative law for the Boolean algebra. So commutative law. Commutative law. So in that we are having, let us take two inputs. Okay. So A plus B is equals to B plus A, and another one is A dot B is equals to B dot A. Okay, so let us take the values of this. I would like to draw here a truth table. Okay, so this is A, B. So here in LHS we are taking that 0, 0, 0, 1, 1, 0, 1, 1. Okay, so the sum of this A plus B is equals to, let us take X. Okay, so 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. Okay, and next we'll see B plus A. B plus A I would like to take Y. Okay, so B plus A, that means first we need to multiply, we need to add from B to A. So 0 plus 0, 0, 1 plus 0, 0, 0 plus 1, sorry, here we have to get 1, right? So 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 1. So here what happens? These two are getting equal. So X is equals to Y. So for that reason we can say the LHS is equals to RHS here. Yes. So here what happens? The commutative law is valid for Boolean algebra. Okay. Next we'll see A dot B is equals to B dot A. Okay. So similarly same thing let us take here. Just draw the truth table for this also. Right. So A, B, B, A dot B, B dot A. So let us write 0 0 0 1 1 0 1 1, right? So 0 into 0, 0 into 0 is 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. Right? Let us take from B into A. B into A means 0 into 0, 0, 1 into 0, 0, 0 into 1, 0, 1 into 1, 1. So here what happens? LHS is equals to RHS here also. So for that reason we can say the commutative law is valid for the Boolean algebra. Okay, next we'll see the associative law. Next we'll see associative law. Associative law. Okay, so in associative law, first we have to know that A plus B plus C is equals to A plus B plus C, or A dot B dot C is equals to A dot B dot C. Okay, so let us do for addition first. Okay, the truth table for the addition here I would like to take here only. A, B, C. Here we are having three inputs, right? Okay, right. A, B, C. Okay, so here we are having A, B, C. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Let us draw again. Here also it will be increased. The number of inputs will get 2n minus 1. So here we are having 3 inputs. So for the result we are going to get the number of inputs are 2 to the power. Here we are having 2 power n, where this n is the number of inputs. Then here we are going to get the number of outputs. That will be equal to, here we are having 3, 1, 2, 3, right? So 2 power 3, that is equals to 8. So we are going to get 8 here, right? So 1, 2, 3, 4, 5, 6, 7, 8. So remaining 3 we have to write 1, 0, 1, 1, 1, 0, 1, 1, 1. So here how many? 1, 2, 3, 4, 1, 2, 3, 4. So here total we got 8 inputs, right? Okay, next we'll see A plus B plus C. First we need to write the B plus C, right? Let us take here A plus B plus C. Okay? So here what happens? A 0 plus B plus C. B plus C is how much? 0. 0 plus 0, right? Here we are having 0, 0, 0 plus 0, 0. So the total output is equals to 0. Right? Next we'll see 0 plus 0 plus 1. 0 plus 1 is how much? 1. So 0 plus 1 is 1. And here also we got the 0 plus 1 is equals to 1. Right? Next one is equals to 0 plus 1 plus 0. 1 plus 0 is how much? That is also equals to 1. Then here we are going to get 1. So 0 plus 1. 0 plus 1 plus 1 is equals to 1. Then we are going to get 1 here. And here we are having 1. And 0 plus 0 is 0. 1 plus 0, 1 is equals to 1. 1. 1 plus 0 is equals to 1. 1. 1 plus 1 is equals to 1. Then 1. So these are my outputs of LHS. Now let us take RHS. RHS is how much here? Let us take that A plus B plus C. So A plus B. A plus B is 0 plus 0 is 0 plus C is equals to 0. That is equals to 0. And next here we are having A plus B. 0 plus 0 is 0 plus 1. 0 plus 1 is 1 plus 0. 0 plus 1 is 1 plus 0. 1 plus 0 is 1 plus 0. 1 plus 0 is 0 plus 1. 1 plus 1 is equals to 1 plus 0. 1 plus 1 is equals to 1 plus 1. So the resultant will be equals to 1, 1, 1, 1. and 1. So here you see, here this LHS and this RHS, right? LHS, RHS. So here what happens, this LHS is equals to the RHS. So for that reason we can say the associative law for addition is valid in the Boolean algebra. Okay, next we'll see the multiplication. So multiplication, you do it as a homework. Okay. Next we'll move to distributive law. Okay, distributive law. What happens here? Here we are going to write the distributive law. D-I-S-T-R-I. Distributive law. Distributive law for Boolean algebra. Okay, so here let us state that A plus B dot C is equals to A plus B dot A plus C. Okay, so A plus B dot C is equals to A plus B dot A plus C. Okay, so we will write the truth table for this first. So this is 1 and this is another one is 2. So that is equals to A dot B plus C. This will be equals to A dot B plus A dot C. Okay, so I can do anything. So you have to do one for homework and one for me. I will do in the class. Okay, one you have to do as your homework. Okay, so till now we have done for only addition. So I would like to do this one. So you do it in the homework. Okay, so here I would like to take the 3 inputs. Here we are having the 3 inputs, right? So A, B, C as my 3 inputs, right? So let us write the 3 inputs. That means total number of outputs we are going to get that 2 power n. So 2 power n is equals to 2 power 3, that is equals to 8. This n is number of inputs. Yes, we have discussed just now, right? So A, B, C. A, B, C. And here we are having that this is what we are going to write. We are going to do it, right? So here we are going to write this one, right? So A dot B plus C. Next, A dot B plus A dot C. So this is what we are going to do. Okay. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0. And next one will be equals to 1 1 1. Right. Okay, so here we are having A dot 0 dot B plus C. B plus C is what? 0 plus 0 is 0. So the output is 0. Next, A 0 dot. So we have already discussed something. 0 into something, 0. Right? 0 into something. So here B plus C is coming. So for the reason we are going to get the something only. So 0 only. So here we are going to get that 0. 0 plus 1 is 0 dot 0 plus 1 is 1. So 0 dot 1 is equals to 0. And here also we are going to get 0 dot 1 plus 0 is 1. So this will be equals to 0 into dot 1. 0 into 1 is equals to 0. So here also we are going to get that the 0 value. And here we are going to get 0. 0 plus 0 is 0. So for the reason we are going to get the answer as a 0. So 1 dot 0 dot 1 is 1. Sorry, no, here we are going to get the 1. So 1 plus 1, 1 dot 1, dot is there, right? So for the reason we need to take here. So 1 dot 1 is equals to 1. So here also we are going to get 1 dot 1 is equals to 1. And here also we are going to get 1 dot 1. Okay, so these are the outputs of LHS. Now we'll see the outputs of RHS. A dot B. A dot B means what? 0 dot 0, 0. Next, 0 dot 0, 0, 0 dot 1, 0, 0 dot 1, 0, 1 dot 0, 0, 1 dot 0, 0, 1 dot 1, 1, 1 dot 1, 1, plus We are having plus on all the sides. Right. A dot C. So A dot C. 0 dot 0. 0. 0 dot 1. 0. 0 dot 0. 0. 0 dot 1. 0. 1 dot 0. 0. 1 dot 1. 1. 1 dot 0. 1 dot 0. 0. 1 dot 1. 1. So the answer will be 0. 0, 0, 0, 0, 1, 1, 1. See, LHS, RHS, both are equal. So by this we can tell that the distributive law is also valid in Boolean algebra. Okay, now we'll see logic gates. Okay, so logic gate is a electronic circuit, right? It is having the one or more inputs, but the output is only one. That means here inputs may be more inputs, one or more than one, right? But output is only one, right? So this logic gate works under certain logic. So for that reason we got the topic called logic gates, right? Okay. So we are having three types of logic gates. We are having three types of logic gates. Three types of logic gates. Right. So the first one is the basic logic gates. Basic logic gates. Basic logic gates. So the next one is that the universal logic gates. Universal logic gates. And third one is special logic gates. Special logic gates. Right. So in basic logic gates, we are going to get the three main logic gates. They are NOT gate, OR gate, AND gate. In universal logic gates, we are going to discuss about NAND gate, NOR gate, NAND, NOR. In special logic gates, we are going to discuss about XOR gate, XNOR gate. Okay, so basic logic gates we are going to discuss about NOT, OR, and in universal logic gates we are going to discuss about NAND, NOR. Special logic gates we are going to discuss about XOR, and XNOR. Right? So we discuss about the basic logic gates first. Okay. So the first one here, basic logic gates. Basic logic gates. Okay. So in that, first we are going to discuss about NOT gate. NOT. N-O-T. NOT gate. NOT gate. Right. So the definition of the NOT gate is whenever we give high input, then the output is low. Are you getting? When input is given high, then the output will be low. Or when the input is low, then the output is more. Okay. So here what happens? It is complementing. We have discussed about the complement, right? So it is complementing. So here the input is low and output is high. That means if we are going to give the input as 0, then output will be equals to 1. If we give the input 1, then our output will be equals to 0, right? So here if you take these numbers in a table, then that is called the truth table. Okay. So this NOT gate is having the only one input and only one output. Okay. Right. These are my inputs, these are my outputs. So if we give 0, then here we are going to get 1. If we are going to give 1, here we are going to get 0. Right? So here not get is that the complement. Complement means here we are going to get, if we are going to get A here, then we are going to get the output as 1, 0. Okay? So this not gate is represented by like this. So this is my input, this is my output. Okay, so whenever we are going to give a low input, then we are going to get the output as high. Then we can say that is NOT gate. Right? This NOT gate works under the common emitter transistor. Common emitter transistor. Right? So common emitter transistor, what it will do? It will do when we give the input low input, then the output will be maximum. Right? And when we give our input maximum, then we are going to get the output as minimum in common emitter transistor. Right? So it is also NOT gate also acts like the common emitter transistor. Right? Okay. Now we'll see the OR gate, OR. OR gate. So second one is OR gate. Right. So this OR gate, what this OR gate do? OR gate will do that when it is OR gate will do that when the inputs, any one of the input is high, then the output will be high. Any one of the input is high in OR gate, then the output will be high. Okay, so the OR gate is represented by like this. OR gate is represented like this. So this is our output. Let us take Y. Right? So these are inputs. These are inputs. So input 1, input 2. Okay, so these are my outputs. So let us say this is A and B. Okay, so this will be equals to the Y. Y is my output, right? So Y is equals to A plus B. A plus B. Okay, so here what happened? Here, any one of the input is high, then the output will be high. Okay, so let us take that the truth table of this. So here we are taking 2 inputs. So we are going to get how many outputs? Total 4 outputs. Total 4 outcomes will come. Okay. So then A, B, Y. Y is equals to A plus B. See here, whenever we are giving the 2 inputs or more than 2 inputs, then we are going to get only 1 output. But here we are getting so many outputs, right? But not, but why? Why? Because these are the total probable outcomes, right? So 0, 0, 0, 1, 1, 0, 1, 1. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. Okay, so this is the truth table of the OR gate. OR gate. So it is also called addition gate. Addition gate. Right? It is an addition gate. So here number of inputs may be 1 or more. 1 or more. But the outcome will be only 1 for addition. Okay. Next we'll see AND gate. Third one is AND. AND gate. Right? So here what happens? In this, any one of the input to be high. But in AND gate, 2 inputs to be high. Any one of the input is low, then the output will be low. So here what happens? Any one input is low. then the output is low. But here what happens? Here any one input is high, then output is high. Okay, any one input is high, then the output is high for OR gate. But here what happens in AND gate? Any one input is low, then the output is low. So the diagram for the AND gate is like this. So here this is our inputs A and B. Okay, so this is AND gate, and this is OR gate, and this is NOT gate. Right? So NOT gate is having round shape here, and here we are having that it is curved shape here, OR gate. So in the OR we are having like this, right? O. So remember like that. O is having the curve. So for that reason we are going to get to the O gate is the curvy shape. Right? So here we are having AND gate. AND is A is having straight. So for that reason we can take the straight. Remember like this. Okay. So here I would like to take two inputs. Right? So two inputs and one output. We are going to get the one output. So this is multiplication. So A dot B. So AND gate is also known for the multiplication gate. Multiplication gate. So here what happens? Any one input is low, then the output is low. So let us write the truth table for this AND gate. A B. Y is equals to A dot B. 0 0 0 1 1 0 1 1. Okay, so 0 dot 0 0 1 dot 0 dot 1 0 1 dot 0 0 1 dot 1 1. So here what happened? The probable outcomes are 4 here. The probable outcomes are 4. Why? Why? Because here number of inputs are 2. So 2 power 2. Here we are going to get the 4. So 4 is the probable outcomes of the AND gate. Then we are having the two inputs. So 0 0 0 1. So these are my outputs of the AND gate. So AND gate, any one input is low, then the output is low. Okay, see here we are having low input, low output, low output, low input, low output, low input, low output, high input, high input, high output. Are you getting? Yes. Okay, so it is represented like this. Next we will see the universal gates. Universal gates. So universal gates are two. We are having two universal gates. So first one is NAND gate. And next one is NOR gate. So we'll discuss about the NOR gate and NAND gate first. So how do we take the NAND gate and NOR gate first? We'll discuss. So here NAND gate I would like to draw. NAND. So NAND gate. NAND gate. So NAND gate, it is a combination of NOT gate and AND gate. So combination of AND gate and NOT gate. Combination of AND gate and NOT gate is called NAND gate. So let us take the AND gate here. So it has to be get the two inputs and one output. This output has to be given to the NOT gate. So here we are going to get the output Y. Okay, so let us take A here, B here. So here we are going to get A dot B. But this A dot B is getting complement here. So for that reason what happens? This will become A dot B complement. A dot B complement. So here what happens? This is NAND gate. So it is also be represented like this. Let us draw the AND gate first. Okay, A, B, and this NOT gate is having the round shape, right? So we'll draw here. Okay, so this become our NAND gate. So the value of this will be equals to y is equals to A dot B. So here this form that the NAND gate, right? So let us write the NOR gate. NOR gate. NOR gate. So here what happens? Here we have OR gate and NOT gate. So it is the combination of the OR gate and the NOT gate. So combination of OR gate plus NOT gate. OR plus NOT, we are going to get NOR. Okay, so let us draw the diagram for the NOR gate. So let us take the two inputs A, B. Okay, so here, so this OR gate has to be connected to the NOT gate. So NOT gate having one output, right? One input, right? Right. So here we are going to get the output of the NOR gate. Y is our output of the NOR gate. So here you see, here this is OR gate, this is NOT gate, right? So here we are going to get the output as A plus B, right? So A plus B is complementing the NOT gate, right? So here we are going to get A plus B complement. So here what happens when the inputs A and B is giving, inputs A and B are giving, then the output will be equals to A plus B complement. Okay, so this is our NOR gate and this is our AND gate. So this is our NAND gate, right? N-A-N-D. NAND gate. This is AND gate. This is NOT gate, right? So here this NOT gate, NAND gate and NOR gate are the universal gates. We call these two are the universal gates. Why we call this universal gate? These two are universal gates. By this we can form the three basic gates. We are having three basic gates, right? So the first one is NOT gate, next one is OR gate, AND gate. So we are having three gates, right? So by these NAND gate and NOR gate, we are going to form the three basic gates. Okay, so let us draw the truth table for this NOR gate and AND gate first. Then after we will discuss how to form NAND gate, NOR gate into the NOT gate, AND gate, OR gate. Okay, let us draw the truth table for this NAND gate and NOR gate. So here we are having how many inputs? Two inputs. So if we are having the two inputs means, then how many probable outcomes will come? That means 2 power 2. 2 power 2 is 4. So 4 outcomes should become A, B. So here first we are going to write the truth table for the NAND gate. Truth table, right? So 0, 0, 0, 1, 1, 0, 1, 1. Okay. So here what happened first? Here we are having A dot B. So A dot B. So A dot B. So A dot B means 0 dot 0, 0, 1, 0 dot 1, 0, 1 dot 0, 0, 1 dot 1, 1. Right? Next, here we are getting the complement of this A dot B. So that means here we are going to get A dot B complement. That means here we are getting 0. So 0 means we are going to get 1. 0 means 1, 0 means 1, 1 means 0. So the truth table of this and NAND gate is the complement of AND gate. See, this is the AND gate, the complement is this one, right? Next, write the NOR gate truth table. So NOR gate to truth table is, so here also we are having the two inputs So the number of outcomes will be 4. Right. A, B. Here we are having two inputs, right? So let us write 0, 0, 0, 1, 1, 0, 1, 1. Right? Next here, the output of the OR gate is equals to A plus B. Right? We are writing A plus B. So A plus B, 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. Right? So here we are having the NOT gate. So the complement of this will be equals to A plus B bar. That means complement, right? So here 0 complement is 1. 1 complement 0. 1 complement 0. 1 complement 0. So here this is the truth table of the NOR gate. This is the truth table of the NOR gate. So here this is OR gate, right? This is NOR gate. This is the complement of OR. So for that reason we got the NOR. So this is AND. This is NAND. So you have to remember this. Right? So by this we have seen that the NAND gate, NOR gate, these two are called as universal gates. Right? So we'll see the why should we have to take these two gates as universal gates.